Hey everyone, and welcome. Today we are jumping straight into a really fun Grade 8 geometry explainer titled Parallelograms and Special Quadrilaterals. If you've ever looked at a shape on a screen and wondered what exactly makes it tick, or how mathematicians rigorously categorize these figures without just guessing, well, you are in the exact right place. We're going to explore the absolutely fascinating world of parallelograms and their very special descendants. Here is a quick look at our agenda for today. First, we'll map out the quadrilateral family tree. Then we'll learn to trust marks over looks. After that, we'll dive into definitions versus sufficient tests, do a couple of pause checks to test your new skills, and finish up with a recap and a transfer question. Let's dive in. Section 1. The quadrilateral family tree. Looking at the quadrilateral hierarchy. Okay, so the crucial thing to understand here is that this hierarchy works exactly like a family tree. Think of the parallelogram as the parent shape. It's fundamentally defined by having opposite sides that are parallel. Now, this parent passes those traits down to its siblings, the rectangle and the rhombus. They inherit all those parent traits, but then they add their own unique specific features. And right at the bottom, we have the square. The square is basically the ultimate child because it inherits absolutely everything from both the rectangle and the rhombus. This setup brilliantly illustrates a core standard in geometry. As the math standards tell us, attributes belonging to a category also belong to all of its subcategories. So we get this golden rule of inheritance. All squares are rectangles, so all squares have 4 right angles. That's why a square can be perfectly described as just a very specific type of rectangle. It literally absorbs all the family traits. Moving on to Section 2. Trust marks, not looks. In geometry, we always have to stick to the core mathematical practices. And today, we're focusing on practice 6. Attend to precision. We're acting like geometry detectives today, which means we have to construct viable arguments based on hard, concrete facts, not just assumptions based on what a shape sort of looks like. Precision is literally everything here. Think about this comparison. On one side, we have what your eyes see. Let's say you're looking at a perfect polygon drawn in software like GeoGebra, and it looks exactly like a rectangle. But on the other side, we have what the marks actually say. If there are no right angle or parallel line markings explicitly drawn on that shape, we absolutely cannot assume it is a rectangle. You can never trust the eyewitness testimony of your own eyes in geometry. If the geometric marks aren't there, the properties aren't there. End of story. Section 3. Definitions versus sufficient tests, where we talk about proving identity. Let's start with our baseline definition. A rectangle is a parallelogram that features 4 90-degree right angles. That is its absolute purest, most fundamental definition. But, here's where it gets really fun. We don't actually always need to find all 4 right angles to prove a shape is a rectangle. Instead, we can use what's called a sufficient test. For instance, high school geometry standards tell us that if you already know a shape is a parallelogram, just finding out that its diagonals are congruent is enough evidence to prove it's a rectangle. Proving a sufficient test guarantees the shape's identity without you having to go around checking every single angle. It's basically a legally approved geometric shortcut. And similarly, let's look at the rhombus. The baseline definition here is simply a parallelogram with 4 sides of equal length. That is the core requirement. If you can prove that or find a sufficient test for it, boom, you've cracked the case. All right, Section 4, Test Properties. It's time for our first pause check. Okay, detective. Here is your question. If a parallelogram's diagonals bisect each other, is that a sufficient test to prove it is a rectangle? I want you to literally pause the explainer right now, think about the clues we just discussed, and decide if this piece of evidence holds up in court. Okay, welcome back. Let's walk through the reasoning together. First, we identify our evidence. The diagonals bisect each other. Second, we recall our basic parallelogram properties. Wait a second, actually, all parallelograms have diagonals that bisect each other. So what's our conclusion? This is absolutely not a sufficient test for a rectangle. Remember, a rectangle specifically requires you to prove that the diagonals are congruent, not just that they bisect each other. If you caught that trap, fantastic work. Round 2, Section 5, Naming Shapes. Here is our second pause check. Here is your challenge. Based only on geometric markings showing 4 congruent sides, what is the most specific name for this parallelogram? Go ahead and hit pause again, and remember our golden rule. Trust the marks, not the looks. All right, we're back. Let's see how you did. Step 1, we observe the marks. We can clearly see 4 congruent sides are explicitly marked. Step 2, we check for other marks. Are there any right angle markings? Nope, 0. So, what's the conclusion? Because we cannot legally assume right angles exist without the marks to prove it, the most specific name we can give this shape is a rhombus, not a square. Even if the shape perfectly looks like a square to your naked eye, without those right angle markings, it is just a rhombus. Section 6. Recap and transfer question. Let's do a final review. Fantastic job today, everyone. Let's summarize our detective's recap. First, always keep your family tree hierarchy in mind. Squares inherit traits from both rectangles and rhombi. Second, follow the evidence rule. Stick rigorously to explicit geometric markings for your evidence, and never, ever rely on visual appearance. And finally, use your tools. Master your definitions as a baseline, and use your sufficient tests to efficiently construct viable arguments and prove a shape's true identity. I am going to leave you with this final, somewhat provocative thought to ponder. Stepping outside of the parallelogram family entirely, if you apply these exact same detective rules to other polygons, like kites or trapezoids, what specific markings would you look for to prove their identity? Think about what sufficient tests might exist for them. It's a great puzzle to solve. Thanks so much for joining me on this explainer. Keep looking for those geometric clues out there, and I will see you next time.